Okay, we'll get started. It's noon. Hello, everyone. Thank you for attending our webinar for this month. Today I have Evan West, and Caleb Burgess from Marel Power Solution. Caleb is a systems engineer, and Evan is the VP of Mechanical Product Engineer at Marel Power. Today, both of them are going to be talking to us about how Marel Power Solution has redefined on how to build and deploy the silicon carbide power stack. So I'll pass it to the both of them to start the webinar.
Awesome. Thanks for that introduction. I just want to make sure that you guys can hear us.
Yes, we hear you.
Perfect. So I'm Evan West, and then this is Caleb, and we'll get right into it here. Slide wants to advance. One moment.
There we go. So who we are as a company, Marel Power Solutions is a startup out of Plymouth, Michigan, just outside of the Detroit metro area. And we are a company that is really focused on bringing high energy density power electronics to market. So this slide here, right, everybody's familiar with the semiconductor vendors. And, you know, there's a little bit of a gap there before you get into your power converter manufacturers. And so this slide here is talking about kind of where Marel sits in this range. So we can work with any die vendor to then build out our own power packages. You'll see in just a little bit what we call our Trident package, right? Fully packaged silicon carbide, but also we can package other technologies as well, such as IGBT devices in there as well. And so in traditional kind of architectures, right, a lot of your semiconductor vendors will develop their own power packages, and you know, some of them will even develop their own power modules. And then on the power converter side, those companies have to select one of those power modules to then build up their architecture with. With our modular design, we are able to swap in different die counts inside of our power packages with the same mechanical footprint to allow a greater flexibility for power converter companies to really dial in which die they want to use, the number of die, without having to go to kind of these bulk different categories. Allows them to switch between die vendors very quickly, switch between different voltage ranges and different generations of die as well too. And so kind of how we do that here is through two kind of core pieces of that modularity. The first one here is what we call our Trident device. It's our power package. It's roughly a TO247 package, but instead of having wire bonds through it, we have a double-sided package, non-isolated. So both heat flows out both of the paddles and current flows out of the paddles. By doing it this way, by not having current carrying wire bonds, we're able to achieve a really, really low inductance. So you'll see on this chart here that we're significantly less than 1 nanohenry of inductance through these devices. This device also currently contains 4 silicon carbide die. Most of what we're building with right now is Gen 3 die, but we also have worked with die suppliers to start packaging Gen 4 silicon carbide as well. And so if you go back one slide real quick, the other thing that I want to point out here is because we're extracting both heat and power through both faces of the die, we're able to achieve really, really low thermal resistance in these packages, where each package itself is less than 0.02 degrees C per watt. So really, really low resistance, low inductance, and low thermal resistance in there as well too.
Yeah, and just to reiterate one thing Caleb touched on, but just to drive the point home is you'll see we still have your typical gate, drain, and source leads coming off the package, but those are really just used for sensing and signaling. They're not current carrying.
They're now just Kelvin connections,
Yep.
allowing for better measurements of RDS on VDS to run your control algorithms with as well too. And then, as we mentioned, they are non-isolated packages, so that means that we do still need that isolation somewhere. And so you'll see in this graphic on the right, we have dielectric coolant tubes. So these tubes are where our isolation layer is, but this allows direct connection of the power packages to cooled bus bars. And these bus bars are also, again, conducting both heat and electricity through them. And so, yeah, as Evan is showing right now, the current flow and the thermal flow both operate through these bus bars, again, allowing us to reduce the V plus to V minus parasitic induction here. So really good heat transfer, really good current transfer. And so in this specific configuration, if you'll go one more, is our half bridge system. So 3 bus bars, because we're doing double-sided cooling, we're cooling both switches in this case through this methodology. And then we also have incredibly large amounts of cross-sectional area to allow for current flow through these devices. So you'll see in this configuration with using 2 tridents per switch, we're able to achieve 850 amps DC under continuous operation, allowing for 105 amps per die of Gen 3. So incredibly powerful utilization of the die with incredibly low parasitic induction and conduction losses.
Yeah, and so what a lot of this drives the overall product to is it's very lightweight, it's very modular, which I'll touch on in a moment, and it's incredibly material efficient. So we can get up to a 4x increase in semiconductor packaging density this way, and that's really what allows us to do that is really the cooling capacity is sometimes 2x the amount of heat we can pull out. So this all leads to, a reduction in weight and volume of up to 50%. You use fewer semiconductors compared to traditional solutions. It's faster to market, faster to prototype thanks to the modularity, and there's a cost savings. So today we're 4 times the US DOE power density target. We've got 5 patents awarded around this technology, and we've passed some key testing out of the AQG 324 test specification. So touching on that heat extraction, this is a chart showing junction temperature versus switching current in amps. And you can see Marel's 5-die technology today matches the performance of what would normally take 8. If we extrapolate that out, we can get up over 800 amps with an 8-die current Gen Tech. So this allows you to reduce the die count in your applications, which usually leads to a large cost savings in addition to the packaging savings. So really, I touched on the modularity, and there are 2 fundamental building blocks of this modularity for us. One of which is the power package, that non-isolated double-side cooled power package, which Caleb already introduced you guys to. And the other big building block is our bus bars, our cooled bus bars and phase bars. And so I want to talk a bit more about that modularity. A unique thing with the power package is the modularity really starts inside the package itself. So this package was designed from the ground up to really be diagnostic. So we can package die from several different manufacturers as well as different die technologies in this same package. And the application, the other thing we can do with this package is within that package, we can populate a different number of die, anywhere from 1 to 4, depending on the die size. And they're just populated or omitted based on the application demands. But no matter the configuration, the external packaging and manufacturing steps remain unchanged. So we have this this unit, this power package unit that is very modular. And another thing I wanted to touch on, so this is a graph of RDS on versus temperature of several different die from different manufacturers. And having that diagnostic power package allows us to get an apples to apples comparison of different die across different manufacturers. And an interesting thing I'd like to point out about this is the top two lines on this graph, kind of the green and purple lines, are actually die from the same data sheet. They're just two different bins. And so this really allows you to, on a data sheet, typically you're limited by thermals, is the limiting factor to characterization. And we're no longer, we are removing that constraint. And, a big advantage here is that a die manufacturer can really demonstrate what their die can do and get an apples to apples comparison with other die in the industry without having that question of what impact the package is having on that performance. Going back to those building blocks of modularity, I said the bus bar and the phase bar are a big part of that. And the sizing of your overall package is sort of determined by the current requirements. So here we see what we call a three-phase single. So it's only two power package of these Trident power packages per phase, one per switch. And the bus bar lengths are sized accordingly. But if we have a higher current application, all we do is increase the length of the bus bars and add two of our Trident power packages per switch, so 4 total per phase. But the important thing to note here is that the manufacturing assembly methods and steps remain more or less unchanged between these. So it's the same power package and the same cooling structure, just enlarged to handle the higher current. So you can take this one step further and open up a couple different avenues of flexibility. For example, this is a 5-phase single where we have 5 individual phases with one power package per switch. And another thing that we can do is even split V plus and V minus bus bars as shown in this example. But again, the modularity continues with even doing this, our assembly methods remain unchanged. So this isn't just something that exists in theory. So we've been through some key AQG testing. So we've passed a shock and vibration profile that's actually an on-engine random and sinusoidal vibration durability test. With little to no degradation. We've taken the same unit and put it through a mechanical shock test. So that single unit has experienced 10 shocks in 3 different axes at 50, 75, and 100 Gs with no degradation. We put the units through a thermal shock test, 1,000 cycles from -40 to 95 C. Passed that with flying colors. High humidity reverse bias testing also passed. And 250,000 power cycles from 25 C to 175 C. The images you see up here, we have a small motor test bench that we've been using to spin some motors. We've got one motor. These are actually motors out of an old Nissan Leaf. We've got one motor acting as a load and one as the drive. And just as an example of the packaging savings, you can see a white outline on motor number 2, which was the size of the original inverter, and the pink outline is the Marel power stack and inverter, which is a huge savings in space. So I'm going to pass it back to Caleb to talk a bit more about some of the specific variants we have.
Yeah, so talking again about kind of this modular design aspect and trying to bring economies of scale, not just to, automotive applications, but to, smaller inverter applications, power conversion applications. We've taken a lot of effort and care to build up are essential building blocks of even full stacks to make sure that they're able to be used for a variety of different applications with minimal adjustment. So the first one, what we've dubbed Titan, is our primary target is high density automotive variants, but think larger passenger vehicles, heavy equipment into industrial use. So this is two power packages per switch for up to 8 die total. With that, and we'll see a picture of the actual one that we've built up here in a second, we're able to achieve 800 amps DC per switch, and that's with Gen 3 die, and that's at 800 volts of operation. 70C, we're looking at 1 kilogram and half a liter for the power stack itself. Obviously, you still need a DC link capacitor in there, so that brings your volume up a little bit. But we're still looking at 800 kilowatts for an incredibly small power package. And if you want to advance the slide, and this is what it looks like, right? So that is a standard can of Coke next to it. And we're pushing 800 amps DC through each one of those phases. We have a variant of this that uses Gen 3 Plus die, and that is able to push some truly ludicrous amounts of current through it. But all of this is designed again with general automotive specifications in mind. So liquid glycol, we're using an 8 to 10 liter per minute flow rate, 15 kilopascals pressure drop across it, very much in line with what a traditional automotive OEM is looking for here. And then on this idea of scaling up and scaling down, Evan showed the single version. This is our quad version, what we've dubbed Athena. It is primarily targeted towards defense and heavy vehicle. And so because of that, all of the numbers here are based off of 105 degree C max coolant temperature. And so with that kind of higher coolant temperature, we're looking at 1200 amps DC per phase, again at an 800 volt operation. This is currently being built up, so we only have CAD models of it right now, but you can see that same base structure. Now the bus bars are wider, and then there are 4 tridents per switch, allowing again for a higher scalability there. As mentioned there, that what we've dubbed Athena, prototypes will be available 2025 as we kind of build out this catalog and repertoire of what we're building. And then for more industrial applications and switching applications, we have a little bit of a lower current variety. So as Evan previously mentioned, these are 5 phases or 5 half bridges, if you would, that are able to be individually controlled. Because of the better heat extraction and because of the low inductance, we're able to switch these faster than some of your traditional packages. Obviously, you still have the same constraints as always, and snubbers and soft switching will always help to increase this further. But the lower inductance means that you have a lower buildup at your higher frequencies. And so this option here is looking at kind of more grid tied uses, along with any number of other uses where you're requiring more than 3 phases. We have a whole bunch of ideas in mind for this, but ultimately we want to make sure that we provide a base set of building blocks that are interchangeable for our customers to be able to use and to build to their specific system requirements.
Yeah, and so continuing with the theme of, this isn't just an academic project. So we're located just outside of Ann Arbor, Michigan. That's where our R&D lab is. So we're very local to the Detroit area, engaging with customers, and we're here to support them. So we've got about 2,300 square feet of secure dedicated lab space. We've got 9 wet benches, our motor test bench, which I talked about briefly earlier. We've got a metal fabrication and mill room, office space, and the capability to make and test everything we've talked about today, and with room to expand as well. We've also got a pilot line at Linamar in Guelph, Ontario, which is about a 3.5-hour drive from our offices. Linamar is a global automotive parts manufacturer. They're a huge company, $7.2 billion in revenue in 2023. They've got 26,000 employees with 67 manufacturing locations, 14 R&D centers, and they've got a footprint in 17 countries. Our pilot line here at the Linamar iHub in Guelph is located inside of a Class 7 clean room. And the money for funding that pilot line was a grant from the government of Ontario. So yeah, this has been an incredible help to us, to get out of just that academic startup world and be producing parts in a pilot line with production intent equipment and processes. I mean, we've had this pilot line up and running for a little over 2 years now.
I think the other important thing to highlight here is, as we talked about earlier, with the ability to package a different die, this pilot line now, we have used over 5 that I know of different die in these power switches. From a variety of different vendors. Sometimes they've been customer inquiries about, hey, we're thinking about using this die. Can you build up a few power packages for us, see how it fits in? Sometimes it's been the die manufacturers of, hey, how hard can you push these die? And so this pilot line really allows us to have that ability to quickly turn parts and quickly, make these research and development samples, along with have good process control for more like product forward devices as well too.
Yeah, great point. So we've got evaluation kits available now. So what you see on screen is our operational half bridge, what we call an M1 eval kit, which is really used if you're interested in getting this technology into your lab and evaluating it. This is a great option for that. This is fully capable. It's got 6 die per switch, 800 amps continuous DC at 800 volts. And we've also got what we call an M3, which is a 3-phase eval kit. So if you want to do more than just evaluate it on the bench, if you want to drive motors with it, that's a full 3-phase 800 amps, 800 volt evaluation kit. So these are available now. And if you want more information on this, it's info@marel-power.com that you can reach out to. And unless Caleb has anything he wants to say here.
I think the big thing here with these eval kits is we know we make some very bold claims, especially about our DC currents that we're able to run through these. So we want to make sure that we're being fully transparent with anyone who's interested, that our technology really does do what we say it does.
Yep.
We also know that based off of the stack up in the very beginning of having a non-isolated package, goes a little bit against what everybody else is doing in the space right now. But we're able to show that you can hit this with a high pot test and be satisfied that the dielectric strength of those tubes that we mentioned earlier are able to withstand everything that you're going to hit them with. That the inductance is truly as low because we're doing that double-sided attach on those die. We're able to have such a comparatively large cross-sectional area of a current carrying path that we're able to cut down on that parasitic induction. We want to make sure that we're really allowing everybody to take a look at the technology and evaluate it for themselves.
Yeah, great point. Yeah, so that brings us to the end of our presentation. I just wanted to thank everyone for coming and thank everyone for your time. And I believe open it up for the Q&A session.
Thank you, Evan and Caleb. Both of you did finish the webinar little fast. So
Yeah.
we have a lot of time for Q&A. So let's wait and see if we have any questions coming in. I do have a question about if the slides will be available. The slides will not be available, but the video recording will be posted on Power America's webpage.
Perfect.
Yeah. So if anyone have questions, please type your questions on the Q&A box.
What are the primary applications that you're trying to get your power stack into first?
So, being Detroit boys, we're surrounded by the auto industry. So that's definitely one of our target applications is the automotive and electric vehicle, hybrid vehicle space. Another one that we're very interested in is the kind of power conversion side. We're seeing a lot of interest in everything from power supplies of data centers, where we're trying to kind of condense the footprint of data centers, really extract as much performance out of these data centers as possible. And so we've had a fair amount of interest there. And then one of the other applications that we didn't necessarily talk about here is solid state transformers. We were selected as part of a DOE competition looking at high voltage DC transformers for essentially DC transmission line applications.
Yeah, and to elaborate on a couple points Caleb made, we've seen a lot of interest in this technology in that data center space. With AI growing and growing these days, data centers are consuming more and more power, and they're having to extract more and more heat. And they're seeing a lot of their physical footprints just balloon with this. And so a technology like this that's liquid cooled and very compact and can be mounted much closer to the point of consumption and extract that heat, they're very interested in. And then the other thing on that we've seen some interest in is solid state switching. So like big DC battery contactors or circuit breakers. So if I go back a couple slides just to illustrate this, you can imagine that if you removed that center phase bar and only had a single row of power packages, so you just had a row of power packages sandwiched between a V plus and a V minus, you can have a very high current DC switch that way. And so that's another application that we've seen a fair amount of traction in. So a bit of a long-winded answer to your question, but hopefully that answers your question.
Yeah, that's good. I'm glad you're looking at the potential for use in data centers.
Yeah, we're very excited about the fact that at the end of the day, what we really build are half bridges. And so, there's a lot of interest and there's a lot of applications, all across the electrification space, as we see these currents and these powers start to increase or really take off in some cases, that we're able to kind of help fulfill all of these different needs where, at the end of the day, everybody wants cheaper, right? Electronics. Everybody wants higher performance out of their electronics. And so as much as we like to geek out about the math and the science and, the performance that we're able to extract out of each die, there's also a very compelling argument of the die reduction there, and being more efficient with our die utilization.
Thank you, Evan. So we do have some questions that has come in. The first one is, what's the highest switching frequency to date?
As of right now, the highest that we've switched is about 100 kilohertz. We have a test that I need to run here very shortly. That one of our specific units is designed to switch up to 200 kilohertz. And so that's a test that's currently on my to-do list, but it has been designed for.
Okay, thank you. The next question, can you tell more about the two-phase dielectric coolant being used and properties?
So an important clarification here is the coolant itself is designed for either water or water glycol. Where our technology lies is the dielectric tubes that surround the coolant here. So the coolant, again, off-the-shelf water glycol, and then the tubes here are actually what contain the dielectric. We have a few applications that we've looked at where, maybe we could use a dielectric coolant. However, none of the dielectric coolants that we've looked at have the same thermal properties or thermal extraction capabilities as water.
Even a lot of the purpose-built dielectric coolants, when you compare them to a water glycol solution, compared to water glycol, a very poor thermal conductivity. And so you can't, to Kayla's point, we've investigated using those, but we've found that using a cooling tube with dielectric properties and flowing a normal water glycol through it is a better approach for most applications. And one thing to mention, is these dielectric coolant tubes are what they are is aluminum nitride at the moment. That's our lead product for these. And so, as a lot of you may be aware, aluminum nitride, while it is electrically isolating, is still very thermally conductive. And so, it's not a plastic tube that passes very little heat. It's a very thermally conductive tube. And so
the key takeaway here is by moving that dielectric to the lining of the coolant channels, that gives us a significantly higher effective cross-sectional area for heat transfer to be applied. Versus some manufacturers are doing a copper and aluminum nitride laminate substrate for their paddles. By pulling that dielectric layer out to the coolant, we're able to have a significantly larger cross-sectional area of it, allowing us to compensate for that reduction in thermal conductivity.
Right. Yeah. Great point.
Okay, thank you. Next question. Placing the modules on the bus bar eliminates separate heatsink. Is that correct?
So the bus bars are copper or aluminum, and the power modules are soldered directly to those bus bars.
So I think to answer the question directly, that is correct. There is no auxiliary heat sinks that have to get attached to the power modules itself. It is a coolant loop. So somewhere in the system, you'll need a radiator, but it is designed in such a way, especially, again, using the water glycol versus a dielectric fluid, allows us to be able to be dropped into a lot more existing applications with minor changes to the coolant loop system.
Yeah, so for like an automotive application, this is just integrated into the vehicle cooling system. It uses the same coolant the rest of the vehicle would use.
Okay, thank you. Okay, next question. Has any short circuit characterization been performed at the switch level and at the interval level? Could you comment on role the ultra low inductance would play in the current derivative dIdt?
Yes. So we have done testing for short circuit protection. This the testing that we've done as part of the AQG highlights was specifically on the module level, though, and that was using DSAT protections that are on our gate drivers in there, and they were specifically tuned to detect with kind of the characteristics of these specific modules. So hopefully that answers your question. Or I guess to further clarify there, with your short circuit fast pulse, your conduction losses are still playing a larger role in your detection voltage rather than your DIDT inductance voltage that's being generated. So we're still able to detect short circuits, and we're still able to do that mostly through DSAT. But we have tested it at the module level.
Okay, thank you. Okay, next question. Any plans for expansion to higher voltage applications?
Yeah, Caleb touched on that a little bit. We're currently going through an R&D project to be able to use. You can elaborate more on the specifics, but yes, we're working on. I believe it's supposed to go up to 20 kilovolts, and that's for grid tied transformer kind of tech. So, who was that funding through?
That's through a U.S. Department of Energy competition that was being held.
Yep, yep.
All of that information should be available to the public.
Yep.
If you search our name and the Department of Energy. For that uses a slightly different architecture than what we're presenting here. It does still use these power packages. These power packages, especially for battery applications, right? We're currently using 1200 volt die. We've looked into, for some customers, using some like 1700 volt die as well. And so we have some scalability there. Ultimately, because the dielectric lays in those tubes, we can alter the thickness of those tubes to allow for higher voltage applications. Obviously, that's going to change the thermal characteristics, so there's some other knobs that we can change there as well too, to allow for even higher voltage applications as we're moving towards kilovolts.
Mm-hmm. Yep.
Okay, thank you. Next question. Any drawback of having non-isolated bases at both sites? Do you eliminate wire bonding completely?
So wire bonding is not completely eliminated because we still need to use wire bonding for our gate attach. But for our current conduction path, no wire bonding. We're right full lug attach all the way through. In terms of the double non-isolated package, all of the benefits that we've seen significantly outweigh the drawbacks, because at the end of the day, we can always, either mask off that other side if we truly needed to, or not have it attached to a cooled bus bar.
Yeah.
So everything there is to say we're quite happy with the double non-isolated, especially with the currents that we're running. Your traditional leads here aren't able to handle anywhere near that current, just because of their small cross-sectional area.
Yeah. Just to reiterate, yeah. So all the wire bonds are out of your high current path. They're just for the gate trigger. And I think, one of the negatives is that, if somebody wanted to get a hold of just these packages, they really need to be used in conjunction with a special cooling structure, right, that has that dielectric layer inside the cooling structure. If you just took one of these and you stuck it on a heat sink, that whole heat sink is live at that point. So yeah, that's really, it's not a negative for the performance of the thing. It's just there's special considerations that a non-isolated package needs if it's used outside of our cooling structure.
Evan, can you hear me?
Yeah, we can hear you now.
Okay, next question. What limits the ability to scale down the size further? Are there any promising technologies to help with this?
So honestly, in terms of scaling down, our biggest limit is dies are integer based, right? So we've looked at doing a single die Trident before, and at the end of the day, we're limited by the physical size of the die. So we can't shrink these packages too terribly much further. And then the other thing that we get a lot of questions about is creepages and clearance. So we are incredibly miniaturized to handle a lot of our creepage and clearance concerns. We already pot the device. All of our 3D models don't necessarily have the potting compound shown because it just makes everything a matte block. But that's the other kind of concern as we move down in voltages, or non-voltages, sorry, down in physical size, is making sure that we still maintain creepages and clearance as our customers require and request. Even this one here isn't fully potted.
Yep. Yeah, I wanted to touch on that a little bit. We removed most of the images we've shown, and even images of actual hardware we've shown have been, intentionally the potting compound has been removed because Caleb's point, at that point it just becomes a black mystery box. You see the inlet and the outlet and the phase connection sticking out, but you can't really see much of the technical goodies that everybody likes to see. So, but yeah, a lot of that, there's some physical design considerations that address some creepage and clearance areas. There's certain isolation sleeves that aren't shown, and then an overmold that addresses most of that. But to Caleb's point, if you want to maintain, as you scale down, if you want to maintain that 400 or 800 volt or higher capacity, creepage and clearance really becomes a challenge at that point. So.
Okay, thank you. We'll move to the next question. Any plan to sub other conversion configurations?
I mean, we're always open in terms of different configurations, different applications. We're still a startup, so our main application is driving, or our main goal right now is to strive for those kind of higher volume, very common applications. It is true right now that for some DC to DC conversion topologies that aren't half bridge based, right, what we're currently selling isn't necessarily the most conducive to that. And that's something that we recognize and that we want to expand on. But we want to make sure that we have enough building blocks for customers to start with before we start expanding our product line out.
Thank you. Okay, the last question is, how does this affect DC link capacitor size?
That's a good question. So because of the lower inductance, you can decrease your DC link capacitance a little bit. And then the other really interesting part about this is because everything is so compact, we're able to normally place the DC link capacitor so much closer to the devices itself. So our standard, if you go to the M1 photo.
Oh yeah, the photo.
You can see that this DC link capacitor is attached really closely to the power stack itself. And we also have some other applications where that DC link capacitor is, instead of having a PCB that routes those leads, we have some other applications where the DC link capacitor is directly attached to the power stack itself. So that lower conduction path to the DC link capacitor reduces the ESR of that capacitor, which then also helps us further decrease the necessary capacitance value. So the key takeaways, right, are lower inductance means that we have lower amounts of capacitance that we require to negate that inductance, and by allowing the physical hardware to be closer, we can reduce that ESR, making that capacitor more effective.
Yeah, and one thing I wanted to touch on real quick that Caleb mentioned is in certain applications, you know, with specific variants for a specific customer, where we can go one step further on how tightly integrated this DC link capacitor is. So, you know, in this eval kit, it's a screw attach because that modularity and serviceability is important. But we've actually got certain applications where the DC link capacitor is laser welded directly to your V plus and V minus bus bar. So it's very tightly packaged and integrated.
Okay. Okay, we do have another question. Can you please show the location of decoupling capacitors for the module?
Yeah, so our bulk DC link capacitor, this one right here, I can pull is this capacitor down here. So the modules that you've seen in the other slides, right? This is one of our bus bars right here. Our phase bar connection is directly through the power stack, and the V plus bar is on the other side of this with these manifolds attached out. So this DC link capacitor down here is sandwiched essentially directly around the power stack itself.
Yeah, and I think another view might make that make that a little more clear as well. Once I get this put away here. Wants to cooperate. Bear with me just a moment. Let's bring up the annotation again. Yep. As Caleb was mentioning, this is our phase connection here. And then this is V plus. And then V minus. V minus. And then that that DC link capacitor is attached directly to these bus bars.
Another thing that you'll see in some of our other photos here is we have another option as well to do an even closer
You probably just draw it in on.
An even closer coupled capacitor. And that is mounted directly between these closest corners of the V plus V minus bar. And so we, for some applications, have done that before, where the capacitor board, especially for ultra low ESR capacitors, are mounted directly between those two bus bars. So that allows us incredibly close coupled for those, again, further reducing the overall amount of capacitance that you need there. The nice part about those as well is when designed correctly, the bus bars will actually continue to cool the capacitors through those traces and through those leads.
Okay, thank you. Okay, we still have some time, so let's just give it another minute to see if we have more Q&A.
For sure.
While we are waiting for that, can you go back to the first slide so that audience can have your email?
Mhm.
Thank you. Okay, we do have a question. Okay. Do the cooling channels ever experience clogging over long time scales?
So we do, as part of a general system view, require some sort of filtration on the coolant itself. Again, with one of our kind of lead applications being automotive, we follow a lot of the automotive requirements on this. So as long as you can restrict any particles of greater than 1 millimeter in diameter from your coolant, we're able to satisfy everything else. So again, that's a fairly large particulate matter inside your coolant that any screen filter should be able to filter out.
Yep.
Again, right, it should be a drop-in for any automotive system.
Yeah,
Those
yep.
have some sort of filtration in place for their coolant channels.
Yep. Yeah, Caleb's absolutely right. Something in your coolant system just shreds itself and you end up with, big, large metal particles flowing around your coolant system. We're not immune to clogging, but those particles really have to be, 1 millimeter or greater for it to become a significant threat.
Okay, thank you. Okay, we don't have any other open questions. So thank you, Evan and Caleb. Thank you for taking the time and to answering all the questions. And to all the attendees, you can take note of their email address, which is stated on the slide. Oh, wait, we have another question. Okay, we just have a comment. It's a nice presentation. Thank you, Stephanie.
Thank you.
Of course, thank you.
Bye-bye. Take care.
Yeah.